determination of element property, that is stiffness matrix. So determination of that stiffness matrix, it involves differentiation and integration process. That differentiation and integration process, it becomes easier the moment you choose this natural coordinate system. That's all. Nothing other than that. If it is regular, global or local coordinate system, it becomes little bit difficult or little bit time consuming one for integration process and other things. Otherwise, if you choose resort to this natural coordinate system, it becomes very easy. That the process of integration, that is for finding strain, which involves differentiation, and integration, which involves determination of stiffness matrix or strain energy concepts. So it involves integration. So that process for finding the element as properties, so this coordinate system is chosen, and we represent the displacements, mainly unknowns, in form of natural coordinate system rather than these other two varieties, which we follow in our classical approach. In classical approach, we followed these two systems using transformation method. Now we are following this natural coordinate system. That is one difference you have in this finite element approach. So I will define what is meant by this natural coordinate system and what are the relationship between the local or global coordinate system with this natural coordinate system. So the global, local and natural coordinate systems coordinate system. So the three forms of displacement. So with respect to coordinate system, for one-dimensional element, I am talking about only one-dimensional element, not 2 and 3. The triangle elements, quadrilateral element, so that I will leave it because it is not in the scope of syllabus. Right? I will take only the 9 elements. Maybe single first order, or it may be quadratic, or it may be cubic maximum. And of course, isoparametric, it is only a subtype. The moment that shape function is used for defining geometry, that is called isoparametric variety. Nothing other than that. So you consider a line element of length L ij length of length L and of course this is not used as writing as initial, that's all. It is not being used here while defining the coordinate system, but simply I am writing, that's all, nothing like that. So like that. An element having one node. Nodes are very important. Line element having 2 nodes. No internal node, first order element. The global coordinate, I will choose this. Like that. That is global x, global y. Right? So bar element. So there is no difference between local and global at all. So it is same. And I will call this distance as x, I. is as x j. Coordinate of I node xi. Coordinate of j node is xj. Because it is only a line element, only one coordinate along the x direction is required. If it is a two-dimensional element, two coordinates to represent any point xy. If it is three-dimensional, three coordinates. Here we are talking about only one coordinate. Right? So, let this be the local origin, middle of the element, O dash. This is O. O is global coordinate origin. O dash is local coordinate origin. Local element. I will choose for local coordinate. I don't say local coordinate. It is called natural coordinate origin. Natural coordinate origin. Local coordinate origin will be one of the nodes same and J. This is your local coordinate system with prime x dash y dash. This is what we have adopted in classical approach. The x coordinate x dash will come y as y coordinate. This is along the axis always. Other two are orthogonal. Here it is always horizontal. So this is global coordinate system. Global system. This is local system. Local coordinate system, where one of the end, usually the left end is chosen as the origin, and this is your L. So that means here xi will be 0 and xj will be L. That's the chain between this global system and local system. For the same element aj, I am representing in different coordinate system. This is global system having origin somewhere. That is the x coordinate. Here local, these are the coordinate, and this is your O dash. That for natural coordinate system we select the center as the origin. That's why I have written here origin for natural coordinate system. Always here. I am representing it. So this is any point in the element. So the global coordinate of any point in the element is x. Correct? This is, there is no difficulty in understanding different coordinates. Here, the same A, that is also x. This is x. X is measured from the local coordinate origin. Here both the coordinates will have units, maybe in centimeter unit or millimeter unit or meter unit, whatever it is. It has units. The coordinates have units in both global and local coordinates. This is an important aspect to remember. In natural coordinate system, for the same nodes, for the same element, we represent any point by a system of coordinate. Here, what is the coordinate of A means global coordinate, I will say x is at a distance A from the global origin. Here in the local system, I will say any point A, it is at a distance x from the local coordinate origin. Likewise, we have another system, which is the one which I am explaining, called natural coordinate system, wherein origin is selected at the center of the element always. Center of the element, irrespective of any other point. Center of the element is chosen as the origin. So that is natural coordinate system. So the same element Ij, I will represent it with respect to natural coordinate system. So this is O dash. Any point A within the element, its distance is measured always from the center of the element, natural coordinate system origin. And this is non-dimensional figure. Whereas all these x in both global and local coordinate system, it has dimension. Here it is a non-dimensional figure, right? So this is natural coordinate system. Any point is represented by its location with respect to natural coordinate origin by a figure which is non-dimensional, and that figure I am going to define now. It is psi is defined as, so here this distance, I will call it as x dash in global x, I will call x bar. Here also x dash, I will call this also x dash because there is no difference between global and local. I will call this distance from O dash as x dash. Yet here it has unit, x dash, millimeter, meter, whatever it is, x dash. Then the z, natural coordinate system, I told, it is a non-dimensional figure which is defined as x divided by L by 2. It is a ratio of two lengths. That is called natural coordinate. Half the length, because origin we are selecting at the center of the element, right? And the distance of any point from the center of the element, that ratio of the distance of the x dash is the distance, ratio of this distance x dash and half the length of the element, that ratio, it becomes non-dimensional. Correct? X dash is having unit, L by 2 is also having unit, that ratio becomes non-dimensional figure. So x dash, because this x dash and this x dash are same, global and local. So the ratio of x dash to L by 2 of the length, that ratio I will call it as the natural coordinate. It is a non-dimensional figure. This is what I am defining now. Any point, it is defined by, any point within an element is defined by natural coordinate by a non-dimensional figure which is purely a ratio of lengths. That's called length coordinate ratios. So in general, is it clear now? The natural coordinate system. So you just take down the natural coordinate, the natural coordinate of any point within the element is a non-dimensional figure representing the ratio of two lengths defined as psi is equal to x dash divided by L by 2. So the values of any other point, the value of this natural coordinate varies from 0 to 1. 0 to 1. 0, 1, a fraction, maybe plus 1 or minus 1. Right? So, value of psi varies from minus 1 to plus 1, having psi equals 0 at origin of line element. Psi will be 0 at the origin. So that is here psi will be 0 at j, psi will be plus 1 at I, psi will be minus 1. At any other point, it will be within minus 1 to plus 1. This is called natural coordinate system. I hope I made it clear. And also the relationship between global, local, and natural. So you can write the relationship now between global or local and global. Local and global. In terms of local and global coordinate system. Local or global, whatever it is, half the length of the element is always constant, whether it is global or local system. So ratio of this denominator ratio is constant. Only this, it will be in the local coordinate because it is measured from center of element, local coordinate. Instead of one end, it will be chosen as the center. That's all the change. But that's why we say it's a local system, natural coordinate system of any point within the element is this non-dimensional figure, which is a ratio. It's a local system. Coordinate. A local system. You can call that also as a local system. Only within the element one point is selected as the origin. It is not a global one. In local coordinate system also one point left hand is chosen as the origin. Here in natural coordinate system, point is selected at the center of the origin and any other point will be expressed as just a ratio. Coordinate of any point is expressed as a ratio of two lengths. One length from origin, another half the length of the element. Half the length, standard. Or in general, you can define this natural coordinate system of any point. So this you can remember, this is simple natural coordinate system, you can call it. Otherwise, in general, if you take any point ij this is O dash. Any point A, the coordinates are expressed by two non-dimensional figures, L1 and L2, which are the distances of that point from the ends, from the two ends. Coordinate of this point I need. From that point, what is the distance of one end I? What is the distance of other end? I will call L1. Then this L1 is defined as L1 is defined. Suppose if this is in the natural coordinate system, this is x. Not local coordinate system, this is L. Then L1 is L minus x by L. That is length AJ divided by length IJ. That is defined as the first coordinate. Second coordinate L2 is defined as L2 is x by n, that is length AI divided by length and j. This is actually the natural coordinate system. You take any point within the element, from that point, the distance of the two ends, you take it. The distance of j end is L minus x by L, where x is the distance of the point A in your natural or not natural, local or global coordinate system. So that point distance from one end, local coordinate system, should be known. This is, if you call it as x, this will be L minus x. Correct? Huh? The ratio of L1 is defined as ratio of L minus x divided by L. And this another coordinate is defined as x by L. So any point is represented by two figures L1, L2 as a natural coordinate. Because it's a planar figure, any point is represented by two non-dimensional figures L1 and L2 whose coordinate is defined in this fashion, purely as ratio of length. One is the distance of the point from right end to length. Another is distance of the point from left end. Here, in simple natural coordinate system, it is taken as from the origin, not from two ends, here only from the origin. That's all both are same. But this is what we use, simple xy-beta system. This is general definition of length coordinate or natural coordinate. Generally, you can define natural coordinate system in this fashion. Natural coordinate is a non-dimensional coordinate system of any point which represent the length ratio of any point from its ends. That's all. I have to say in general. It is just a non-dimensional figure. This is a very, very important aspect. Now you know the relationship. This L1 itself is your L1. Here also I can define that N1, N2. N1 is defined as 1 minus psi by 2. N2 is defined as 1 plus psi by 2. That is your shape function. See, this is by same concept, whatever basic concepts I have told. What is L by 2 here? Suppose if you take, I have taken here z equals minus 1, z equals plus 1. Correct? So total length of the element is 2. Minus 1 to 1. Total length of the element is 2. Half the length is 1. This is total length is 2. This is length, total length. This 1 minus 0 is the length of the point from A to other end. That's what I have defined here. You see L1 corresponds to node 1. It is distance of the other end. That is this distance. This is nothing but 1 minus x dash or 1 minus psi. 1 minus psi divided by total length. Total length is 2. While defining a natural coordinate itself, 2. Like that, with respect to this, N2 is this distance. This is 1 plus x, 1 plus z. This is 1, this is z. 1 plus z divided by length. This is 1 minus z by length. This is 1 plus z by length. So this is the ratio. This again is another thing. So this is called shape function. This is also either L1 is the symbol adopted for defining natural coordinate or L1. If you adopt this. This looks a little bit some complicated thing, but virtually it is not so. It is just a ratio. Simply remember the distances either from the two ends or from the origin. That's all you have to remember. Because this is a very, very important concept which we use in deriving the element property. The moment I define this as the ratios N1 and N2, they are called the shape functions. So the displacement at any point of this bar element will be now is N1 into U1 plus N2 into U2, where N1 and N2 are 1 minus z by 2 and 1 plus z by 2. So then you can find the strain, stress and element stiffness matrix of a bar element, which is AE by L 1 minus 1 minus 1 1. You can derive from this. That's all. If you derive that, that is the end. So you can use for proper sum. This is the important concept of finite element analysis. That is one element. I hope I made the things clear. It's a very, very important aspect. Coordinate system, global, local system, natural coordinate system. Natural coordinate system is only ratio of lengths. In two-dimensional, it is ratio of areas. In three-dimensional, it is ratio of volumes. Thereby, this non-dimensional thing, it will help us in integrations and differentiation process. We can get the element property without any problem. Straight away remembering what is that coordinate system, what is that. That's all the entire nerve system of this finite element. Nothing else than that. This was concept, if it goes to your mind, there won't be any problem in understanding. Same procedure for two-dimensional thing also. There, as I told you, ratio of areas I will take. Here, ratio of lengths. Same natural coordinate system, there also I will define. In natural coordinate system, the element we define the displacement model in terms of shape functions and calculate it. Only this shape function for bar or truss element already have derived shape function. But only for beam, it is 2 degrees of freedom, rotation is there. It is slightly a different process. That's called Hermitian shape function. That I have to derive. That we will take up when I take beam problem. Now bar and truss problem already I have derived the shape function and displacement model which represents the displacement at any point. So in natural coordinate system, the displacement at any point A. So here in natural coordinate system, displacement at any point A, say Q, displacement, that displacement at any point Q, now you can express it Q as N1 Q1 plus into Q2, where N1 you know it is 1 minus psi by 2 and this is 1 plus psi by 2. In matrix form I will write or these nodal displacements Q1, Q2. So Q is equal to this I will say as usual Q is equal to this notation is being overlapping. I call this displacement U. Then it will be, there won't be any confusion. U displacement at any point, UVW displacement at any point you will use, and Q is always be used to represent nodal displacement. Q is a nodal displacement vector. Here Q1, Q2 for bar element or truss element in local coordinate system. Right? Bar or truss element in local coordinate system. The displacements of Q1 and Q2 in local coordinate. Q is Q1, Q2. In terms of Q1, Q2, the displacement at any point Q, at any point A, I am calling it as Q. In terms of natural coordinate system, right? And mind it, no, here, coordinate of point I. What is the natural coordinate of point I? Can you tell? Coordinate of natural point I at I, Z is equal to 1. From what actually are measuring the distance? Mind it. Here, Z is measured from O dash. At point I, what is coordinate? Z is equal to minus 1. Z is minus 1. So what is N1? 1. What is N2?
0.
1 minus 1, 0. So natural coordinate of point I, it is 1, 0. Likewise, natural coordinate of the J,
0.
it is 0, 1. Correct? I hope I made the things clear now. Or that L1, L2 also you can use it. That I update also. Any point from here. There also it is same thing. You will get the same thing. So the property, important property of the shape function is that N1 plus N2 or even N1 plus L2, that should be 1 always. N1 plus N2 or L1 plus L2 is always 1. That's a very, very important. Sum of the shape function is always 1. That you can see. The sum 1 minus psi by 2 plus 1 plus psi by 2, it is 1. Psi will cancel, it will be half plus half, it is 1. So that's a very important property you have to observe. And now the variation also, the displacement variation, because I told U is equal to displacement at any point is N1 Q1 plus N2 Q2. So if you plot at node I, displacement will be 1. At node I, psi is equal to minus 1. If you put psi is equal to the minus 1, n1 will be 1, n2 is 0. So n1 is 1, n2 is 0. So u is equal to n1. n1 is 1 itself. So the displacement at node I is 1. Displacement at node j, it is 0. You can verify. So this variation is straight line variation, y equals mx version. So this is your n1 variation. n1 is 0 at j, n1 is 1 at 1, that you have seen. Likewise, n2 if you plot, n2 is 0 at I, it is 1 at j. This is variation of n2 at any point. So n1 will be this, n1, u1, n2, u2. n2 will be this at any point. The variation of the displacement all along the length of the member is straight line variation. It is because it is linear variation. So we can find variation of this displacement. The same variation if you use for geometry, if you define defining say n1, n2, the same type of variation will get an altogether different way of mapping, which will take care of arbitrary shape. That is the isoparametric concept, nothing other than that. That same shape function, it will be used to define geometry as well as displacement for any point, the coordinate of any point or displacement of any point. Same shape functions will be used, thereby we can take care of arbitrary shape, because it is not dimensional, arbitrary shape. So any complicated shape, you can represent it by this representation of finite element. Whereas in classical approach, this advantage we don't have to take care of the regular boundary condition, shape, size, material property and all. That has been taken care by these equations or parameters. Clear? So when once you know the displacement model in this fashion, expressed in terms of the nodal displacement through shape function, you can find strain, which is derivative of this, right? Derivative of this means it is only derivative of shape function. Then stress strain knowing energy, which is integral form, integration, then integration of shape function, then minimization of that will give you element property.